Alyssa Keirn, and today I'll be telling you about my solar-powered decontaminators that I built over a period of about 5 years. These devices are designed to be used in off-the-grid locations to help save lives from foodborne illness. You may not know this, but about 420,000 people die every year from foodborne illness. Of those, about 30% are children, according to the World Health Organization. Back when I was in 8th grade, I started this project with the goal of finally creating something that could be used in these locations to help clean the surface of things like knives or forks, as well as food to help save people's lives. Originally, I started with this device here. At the time, there was a large Ebola scare going on in Africa, and the news coverage caught my attention. I looked into the outbreak, and I found that one of the main vectors was actually hunting knives. People were butchering animals with the same implements, and it was spreading the virus from one meat source to another. So I created this device, which uses UVC light to help clean those implements in these locations. From there, this project snowballed. I realized what a big problem foodborne illness was, and I adapted my devices to try to clean food as well as utensils. My final device, this one here, is capable of cleaning a variety of food items and utensils and killing up to 99% or more of the bacteria present on those items. When I was younger, I didn't really know what I wanted to do with my life. I considered disciplines like biology, chemistry, physics. All of those disciplines have a place in my project, but they're not the main focus. The main focus is engineering. This project has showed me how to solder, how to create circuits, and how to code, as well as a variety of other things that go into an engineering project. All of that has helped me foster my passion for engineering. I know what I want to do with my life now. I want to be an electrical engineer. This is the original device that I created in middle school. It is a very basic design with 2 solar panels here in the back wired to some batteries. When the door is put on, it completes a circuit that turns on a UVC light that's mounted in the top of the tube. This device was originally tested in a lab at Colorado State University on 2 different types of bacteria which were placed inside to prove that the overall design was sound. This is the second device that I built. The big difference between it and the first device is that this one is specifically designed to clean eggs. There's a rotating drum here in the front, which when turned on, rotates the eggs underneath some UVC lights. Unlike the previous device, these UVC lights are much more powerful. When tested in the lab on bacteria, this device was much more effective at decontaminating. This device has several major differences from the previous 2. First off, it uses ozone gas in this chamber here to do the decontamination. That's because in some of my previous tests, I found that the UVC light was not getting into all the cracks and crevices on some of the food items. Ozone, being a gas, can. It also uses a dual-axis sun-tracking solar panel, which is this panel here. The panel works by using 4 light-sensitive resistors arrayed in an X formation to determine where the light source is to tilt the panel. This device also has a Raspberry Pi 3 here in the back that I coded. That Raspberry Pi controls things like runtime, as well as tilting the panel towards the sun. This 4th and final device combined all the best aspects of the previous devices, as well as some new ones. In the end, it was over 99% effective at killing the bacteria on a variety of food items and utensils that were placed inside of it. It uses both UVC light and ozone gas in this chamber here, which was revamped to allow a smaller volume of air while a larger volume of food could be placed inside. It also uses a dual-axis sun-tracking solar panel and a Raspberry Pi. This chamber here is where the food is placed. When the device is turned on, the rack in the middle rotates the food items. This allows all sides of the food items to be exposed to the UVC light as well as the ozone gas. This rack is also capable of being removed to allow people to wash the inside of the container if necessary. This chamber here is kind of the guts of the device. This board here in the center is a Raspberry Pi 3, which has about 1,000 lines of code that I wrote to control several different processes. There are also several relay boards, a few potentiometers, boards for controlling the stepper motors which tilt the panel, as well as a humidity and temperature sensor. Of the many processes that the Raspberry Pi 3 controls, the most important is decontamination. When this green button here is pressed, the device starts a new decontamination cycle. To do that, it reads the value off of this dial here, which tells it which type of food item has been placed inside the box. It also reads the humidity and temperature inside off of a humidity and temperature sensor. This allows it to calculate how long it needs to run. First off, it gives it a base value for the ozone gas. When humidity and temperature increase, the half-life of ozone gas decreases, and so the device has to run longer to compensate. The type of food item tells the device whether or not it needs to add in that extra time for the ozone. For things like eggs, which have a relatively flat surface, the UVC is sufficient to kill the bacteria. When the time has elapsed, the device turns itself off and goes back to waiting for a new cycle to start. It also controls the motion of the panel using this button here. When it's pressed, the panel can either go flat for transportation or sun tracking can be enabled. These switches here allow certain processes to be turned off in the case of transport, such as UVC light being on, ozone gas being on, or the panel being allowed to move. These 4 light-sensitive resistors here allow the device to figure out where the light source is in order to tilt the panel. When one of the light-sensitive resistors detects light while the other doesn't, the panel tilts in order to make it so all of the light-sensitive resistors detect light. When the light-sensitive resistors show that the panel is not pointed directly at the light source, 2 stepper motors, one for each axis, start to rotate part of a linear actuator. This tilts the panel and allows it to get directly towards the sun. After I had built the mechanisms in the decontamination chamber, I went into a chemistry lab at Colorado State University and I tested the intensity of the UVC light inside the chamber at 12 different locations. Each of these locations corresponds to a place where an egg would sit on the rack. Using a luminance flux meter to collect this data, I then made 2 3-dimensional regression graphs of the intensity of the light on top of the rack. The first of these graphs shows the intensity of the light facing upwards towards the lights. The second shows the intensity of the light facing downwards towards the bottom of the box, or all the light that's been reflected off of the bottom of the chamber back up onto the rack. I used the lowest possible value on this regression to calculate how long the device needed to run. I also tested 5 different surfaces of aluminum to figure out which one reflected UVC light the best. My results showed that all of the surfaces were about the same, so I left the inside of the decontamination chamber as it was in order to save costs and get rid of potential maintenance. This shows a set of results from bacteria testing with the 4th and final device. The first 2 rows show tests on Salmonella enteritidis, and the last 2 rows show tests on Staphylococcus epidermidis. These results are for eggs. The bacteria were swabbed on the surface of the eggs. The eggs were then placed through the device and then swabbed again. The swab was placed in a saline solution, which was then plated on 2 different types of agar. The first is TSA, or tryptic soy agar. The second was a selective agar, depending on the type of bacteria. The first 2 rows show the results for enteritidis. As you can see, the positive control, or an egg that was inoculated and did not go through the device, shows growth, while the 3 trials do not. The same is true for Staphylococcus epidermidis samples. These proved that the device worked. In my junior year, I briefly talked with some nonprofits in my area about the possibility of taking this device and putting it into place in the areas where it's needed. Although it still needs some improvements, the person that I talked to agreed that it has potential. It is my hope that as I move into college, I can take my ideas with me to certain organizations such as Engineers Without Borders to maybe market this device and get it into the places where it's needed to help save lives.